All right, guys, let's try this a little bit different. I've made an entire package, some PowerPoints that I have manipulated from the book, and we'll see if this works a little bit better. So, today, Tuesday, we are going to dive into our newest section, which out of the book is section 2.4. I'll try to always do that because some of this stuff comes from the book. And then I'll add my stuff that I think you guys need to know. So we're going to talk about rates of change and tangent lines, which is pretty much a very central idea. Lots of room, hopefully, on your packet to write notes. So we'll see. Okay, so what we're going to tackle today, we're going to tackle tangent lines and then slopes of curves, and then talk about instantaneous rate of change and why. Number one, tangent lines determine the direction of a body's this got a little messed up when I was retyping. Basically, it finds its instantaneous velocity. So, instantaneous change is rate of change is its actual velocity at a point, velocity at a certain point. And so, this is kind of where we start dialing in with physics and some different things. And that's why it talks about a body's point, like a particle or a car or something moving along a certain path. So in calculus, our main concept is instant rate of change, which is the slope. So the rate of change is the same as slope. So the slope of a tangent line is the same as the instant rate of change. And you guys know all sorts of formulas for slope. So really, all we're covering is slope. In this unit in different ways and new ways to find slope. So just remember average rates of change were usually like if I had a line here and a line here and I had all these points in between, let's say, but they said the average rate of change, what we're talking about is this idea that we're going to go from the first point all the way to the last point. And at that point, at that particular time, we're going to, let me make the line just a little bit bigger so you can see it. We're going to find the slope, and the slope is our rise over our run. So we've got, back from seventh grade, we got our rise over our run. And then we do our formulas, but we're just going to worry about calling it the change in y over the change in x. And it's called the average rate of change because it's from the very first to the very last, and you pretty much skip all the stuff in between. Okay, so that's what they're talking about here. It's the interval of amount of change divided by the length. So the amount of change is the rise, and the length is the run. Uh, so we can also look at this, and you're probably not going, what the heck is a secant line? So I'll do my best to draw it here. So let's take a shape here. It won't let me do a curved line on this. So let's just base it on something like this. So let's just take this right here. All right. So if I take this ellipse right here and I keep my same color, but I'll make a line and I'm going to make this one green here. A secant line is a line that looks like that. It connects two spots on a curve. So if you notice, and this spot right here should have actually made it all the way to there. So that's a secant line, and then this right here is a secant line. Now what I want to draw your attention to is, though they're on a curve, look what we got. We've got a run and we've got a rise. So the average rate of change can be thought of as a slope of a secant line when it's on a curve. So we're going to take this idea of nice, beautiful straight lines, and we're going to turn them into a secant idea. Okay. All right. So let's move on to that next thing. So when you find rates of change, this is just kind of a quick review. I want to kind of tackle a couple of things with you guys here. One of them is this. So this is over the interval. Okay. So this means that the starting point, I'm going to put SP for starting point, is at x equals -2. And the ending point is at x equals 4. That's why we do -2 minus 4. That's my run. So I started at -2 and I run over to 4. Okay. Now I've got to figure out what the height is, and I don't know what that is. Well, that is going to be my change in y's. So don't forget, every time I put in an x value into here, I get out a y value. So you won't see it written as y equals. You'll see it as f of something. So f of -2 means that I take the -2 and I plugged it into the original function. That's all they're saying here. So when you see that, don't panic. And then I get that answer, and then I take f of 4, my ending point, and I plug that in here. And so get used to the notation of f of 4, f of 2, those types of things. So we're just plugging it in. So this is literally the same thing as the change in y over the change in x. Kind of seeing the consistency of a certain values that we're looking for, guys. Change in y over the change in x. All right, so tangent to a curve. So in calculus, we're going to define the rate. See, now we're changing the word. Look at this. We're finding the rate at which the value of a function is changing with respect to x at a particular value of x. What is this saying? I don't know. This looks like a foreign language. Well, it is. So what we're really saying here is that a slope of a tangent line. Now, what we talked about is a tangent line. What? Now we're talking about tangents. We were just talking about secants. What the heck is going on? So if I take something like this, let's just take that beauty of a circle. Man, I'm getting good at drawing these. Yeah, okay, whatever. And I go something like this, and I touch the outside edge just like that. That's a tangent line. Something that touches it in one point. Yeah, I didn't get very accurate, but the whole idea is this, is that the tangent line is something just like that. So it touches right here. So this is the tangent line. Touches it exactly perfect, okay? And the tangent is perpendicular to this, and it's got all sorts of crazy stuff, and we'll get to that later, okay? So what we're saying is that the tangent line has a slope with respect to the x value, which is the run, right? With respect to x, okay? It has the rate at which the value of the function y equals, what's the value? It's y, is changing with respect to x. So at a particular point. So this thing would be considered x equals a. Now, a can be any value of x. Okay? All right? So the problem is, like you see here, that you only have 1 point and the slope requires 2 points. So if we're talking about one specific point, how the heck do we find the slope at one specific point? Think about it. Think about it. Has to do with the secant line. You got an idea yet? Well, here we go. So the process starts like this. We're going to take we're going to talk about a secant through a certain point and another point on the curve. So we're going to really work with a secant slope right here. Okay. So the idea is this: is if I have there's a better drawing after this, but I'm going to kind of explain it real quick. The idea is this: if I have my circle here, like that one, and then I have my line like that, right? But we also know that we have a secant line right here. And we know that secant line we can turn into a triangle. We saw it happen before, right? We saw it happen before. We turn this into a triangle like this. And we can take that triangle and we can find its slope. Now, what happens if we start with that triangle, but that triangle repeatedly gets smaller? And all of a sudden, now I got a smaller triangle. And then I do it again and I get a smaller triangle and then a smaller triangle. And then all of a sudden, that triangle is at that exact point that we need. So, what do we call this idea of some sort of function approaching a certain point? It's a limiting value. In other words, we are going to find the limit of the secant line. At point X equals whatever we're looking for. Okay. All right. So here's the idea. So I'm gonna draw, well, this is a U shape. So we're gonna do this. Here's my U shape right here. That's my basic idea of this right here. Okay. Now, I'm gonna draw my tangent line. I'll just do that one. I'm just gonna draw it at -1. It's gonna be a negative slope, so I'm gonna draw it over here. So let's just assume it looks like that. This is not to scale, guys, but it just gives you an idea. And so what we're finding is this. Oops. Let me go back to shapes real quick, guys, and we're going to make this. Let's just do the secant in black. What we're going to find is this right here. So we're going to use the black secant line right here for the tangent. If you guys can see that, I did the same color like a knucklehead. So we're going to have this black secant line right here, and this is going to be H, right? So as this thing gets smaller and smaller and smaller, H approaches 0. Okay? H approaches 0. Now the other thing is that when I break this secant line triangle out, triangle out, we get this idea that this y value is the function. This particular y value is the function of -1 plus the height. Okay, and then the no, I shouldn't have done it that way. It's not the height, guys. Sorry, it's not the height. It's the oh, my brain just went dead. Let me erase that. It's not the height. I think I got to slide backwards, but that's okay. Okay, so let's just assume that this point, let me this is x equals -1, right? Let me go backwards here. Let me go to the next slide. I want to make sure that we got. See, that's the one that I wanted you guys to see, but they use different terminology, so we're gonna work our way through this. Okay, so they kind of throw this at you here. So let's just assume that this is -1, right? And then you get over here, it's -1 plus h. We're going to call that h. You can call it whatever. So my x value is equal to -1 here. And this is my y value, which is going to be -1 plus h. Correct? So, let's just call this h. Or you can call this the change in x. Whatever you want to call this, you're going to see it as h a lot. Okay? So this is going to be considered h. So how do I find my y value? Well, I plug in f of -1. That's where this comes from. Okay? How do I find my y value here? I'm going to plug in f of -1 plus h. That's where this comes in right here. So then this is a formula that they come up with, which is going to be f of x plus h squared minus f of x all over h. So that's where this comes from. It's kind of a formula. We'll go over it in class real quick too. All right. So when you do all that, you got to multiply this out. Don't forget, this is the most common mistake, which is going to be -1 plus h times -1 plus h. And this thing cleans itself up. If it gets really, really big, it should kind of cancel things out, like your 3's cancel here. And then your once you get to this point, your h's cancel. And so the whole goal is to get rid of this, okay? To get rid of that of h. So that way we can plug 0 in to get an answer. So the limit as h approaches 0 of this particular piece is -2, okay? So that's the slope at that particular point. So we do the same thing here. If they give us, this is just giving us some information. So if they give us a tangent line and the slope is -2 and it passes through -1 and 3, we got our y minus y1 equals slope times x minus x1, right? And so we're going to do y minus 3 equals our slope -2 times x minus a -1. And then when we clean that up, there's my tangent line. Okay? Kind of see how that works. So we're going to use the idea of finding the slope to the tangent line. We're going to need to find this. And then we're going to write the equation for what it passes through. All right? Okay. So the slope of the curve. This is kind of the idea that I was talking about before. This slide got a little backwards, so we're going to work our way towards that. So let's look at this. So this is the idea, guys. What they're representing as h is the distance from here to there, the triangle. So what we're really saying is that this is h, okay? And then we have this triangle, this side of the triangle. So this side is represented by x equals a. That's where this comes from right there. So at a, I have to get over to the other x value here. So if I get over to the other x value, that is going to be plugging in, that's going to be a plus what they're calling h, which is the bottom, okay? So now we've got a for x equals a, and we have x2, let's say, equals a plus h. So how do I find my y values that are associated with this? Well, this y value here is going to be f, it's going to be a, and I'm going to have to plug in a to the equation. So f of a. This y value here is associated with the x value of x plus h, so I have to plug in a plus h. Okay? All right. So that's where these values here come from. Point Q is a plus h and f of a plus h. This one here is a and f of a. All right, so what does all that mean? Remember, this is slope, right? So I want to find the slope at these 2 points. So what's slope? Slope is the change in y over the change in x. So what's the change in y? It's going to be f of a plus h minus f of a. I got those two guys from my y values here. Okay? And that's going to be over my change in x. What's my x's? I have a and my a plus h. Okay? Well, if I do that, I get a minus a plus h. right? And so, no, that's backwards. Sorry, guys. I did my points backwards. This is A plus H minus A. Well, the A's cancel, and so I'm left with this, right? And H. Well, what do we know about H of the secant line as it approaches this exact point? As this exact point, this H gets smaller and smaller and smaller to where it's almost zero. So then we add the whole as the limit approaches zero. Okay? So we end up with this piece here. This is the slope of a curve. Okay? So we're going to get f of a plus h minus f of a. I know I'm writing it again. Over h. We just found that. And then we just said, oh, well, we know that the limit approaches zero. And that's how you find the slope of a curve at a point. Okay? So, just so you guys know, the slope of y equals f of x at a is the same as the slope of the tangent line at a, which is the instant rate of change at f of x at a certain point of a, which is this here, which is our limits. Now you know why we're doing limits, and it's called the difference quotient, okay? It's called the difference quotient. And then all of this, if you really think about it, is based on the original idea of slope, which is rise over run, which is y2 minus y1 over x2 minus x1, which is the same as the change in y over the change in x, which is the same as all of that stuff up there. Okay? So it's all the slope of a curve. All right. So normal to a curve is just perpendicular. I'm going to leave that one there. Normal to a curve is perpendicular tangent. So normal is perpendicular to the tangent line. So if we have a tangent line, look, if we have a tangent line, that means my normal is the slope of the perpendicular, which is going to be that this idea flipped over. So -2, we flip it over to make it -2 over 1, then we change the sign to make it 1/2. Oops, sorry. -1 over 2. Sorry, guys. -1 over 2. And then we get the idea of 1/2, which is what we put in here. So when you're given a tangent, just use the reciprocal to make a normal. When you're given a normal, just use the reciprocal to make a tangent. That's all we're talking about on those. All right, guys? So your assignment is here. It's going to be using f of x plus h minus f of, a. It's all the same. Remember, a is the same as x, so that way it's not as confusing, hopefully, over h as the limit approaches, as h approaches 0. That's what we're dealing with right there. We need to work with those things. I'm going to go back up here. When I think I said something earlier. It's right. No. Where'd it go? Oh, the reason I put this squared here, that's what I was thinking about this whole time. As I put this squared here, that squared comes from the original problem right here. Okay? That squared comes from the original problem. All right? All right, guys. A little longer video. That is a theoretical version of the tangent line, and we'll talk about more in a little bit.